I'm going to show you now how do we create a binary tree starting from an empty project. I am going to assume that you know already what is a binary tree. So we're going to go ahead and create the binary tree. We're going to try to create some methods and perform some operations. So first thing I'm going to create my header file. Again, a binary tree will mainly contain nodes. So I need to have structure of a type node. So we'll go ahead and do that. So I'm just going to go ahead and create the node structure. Of course, you can call it binary node structure. You can call it whatever you want. Let's start with the preprocessor. So if n define node underscore h, then define it. node h. Now, just for me to not forget, I'm going to come here and type end if. Okay, so here's my beginning. I'm going to come here, include the IO stream. Now, I just want to make sure that you understand that I am not putting optimization, the performance under my consideration right now. I'm just trying to make it fast, to make it a little bit simpler. So, using namespace std. Okay, I'm gonna, it should be a template, but again, if I'm gonna create a template, it's just gonna look a little bit more complicated. So I'm gonna go with a traditional structure. And I'm gonna call it node. And in this node, we basically gonna have a data field. In those data fields or data members, we're gonna have, I'm gonna create a type of integer. So I'm gonna go integer data. And I am also going to have a pointer to a node. We're going to call it left, and another pointer we're going to call it right. So those are my data members. And now what I'm going to have a constructor. So node, and in this node constructor, we're going to have some elements. So let's say integer, let's go d, and then we will have a pointer, we'll call it left, and another pointer, and we'll call it right. So those are this is my constructor, my default constructor. Not default, actually, argument constructor. Now also we will have a destructure node, semicolon. It's recommended to keep your destructure virtual, and whenever you have multiple classes that you're going to create, and you're going to create a sort of relationship between, especially the one that we're going to have here as a composition, and since the binary tree is going to contain nodes, so we need to keep this to be virtual. This will basically gonna, if we don't use it virtual, you cannot guarantee the order of which nodes or objects are going to be destroyed by the end of the program. So I don't think it's going to be really something you're going to see the effect of it, but it's for optimization. We'll just go ahead and put it that way. Now, after that, I am just going to overload the operation of showing the data, the insertion operation. So I will just say O stream reference operator. And then we're talking about this operation. And let's see here. I'm going to pass an OStream object, reference again, and I'm just going to call it, well, actually, let's go W. And I believe that's all I need. So here we go. This is my structure, as simple as it looks like. Now, I'm going to go inside the sources, and I'm going to create a C file, implementation file, and I'm going to call it node. Now, first thing first, I need to include node.h. And then finally, I need to copy the methods that I have here, which are those three methods. I'm going to put it here. I'll take those semicolon, replace them with the body, take the semicolon, replace it with the body, take the semicolon, replace it with the body. Since I'm going to have to put node, and you put node here as well. Well, since it's virtual, you don't have to type virtual here anymore. And I have to come here and type node, colon, colon. For the implementation, you can use member initialization lists if you want, but I'm going to go with the following. I'm going to try something and see if he likes it or not. Now, actually, I knew it. He's not going to like it. So I'll just take that out. For some reason, I should be able to do this, but let's go ahead and do this first. So this is going to be W. We'll say this dot data, and I'll put semicolon here, and then return W. Okay. In this area, basically, data should be assigned to D, and then we'll see left should be, L should be assigned to left, and then right, R should be assigned to right data. Okay, I'm going to try to modify this, but I just need to make sure that it works with no problems at the beginning. Let me save everything. I'm going to go to source, create a new file, source file, and I'm going to include node. And then here I'm going to create an integer main. And in this area here, come on, what are you complaining about? I'm going to come here and type node and 1 semicolon. No source protocol node. Here it is. Oh, .h. My bad. Okay. So let's create 3 nodes just for the sake of it. Node 1, node 2, node 3. And then here I'm going to say, let's say 10 null with uppercase. And another null. And then here I'm going to put 5 null and null. And here I'm going to say 15, and this time I'm going to say N1 is my left child and N2 is my right child. Yep, why is he not, doesn't like this? This is an integer. Let me take this away for now. I'll try to figure that out in a sec. I just want to say, if I say cout N1 and line, semicolon, well, I just overloaded this. Oh, okay, I think I know what did I do wrong here. I need to actually pass the object. So I will say node reference. Let's say, we'll call it T. So we're going to come here and say T dot data, and of course I have to come and copy this and put it here as well. Operator, why are you complaining? Too many parameters. Okay. Too many parameters. Yep, that makes sense. And then let's just type data. Okay, how come you don't like this here? So we do have issues with those two functions here. Let me just run it to make sure that this works at least. Okay, so that worked. Now we do have an issue with this method here when I try to pass match arguments n1 and 2. Oh, since those are pointers, I need to pass the address. Okay, let's see if that's going to be acceptable. Okay, that's totally acceptable. Let's try to run it now. Okay, this is the only problem that I have here. Let me just try to figure out why is he complaining about that. I need to come back here and type friend. Okay, and I'll just put this as a constant. And let's do the same thing here. Now, constant. And this is where I'm going to type n dot data. Has no member operator. Why is it doing this? Let me copy this. And let's put this here. Of course, I need to take this away. Okay, let's go back here to the source, and now it's working perfectly fine. And here it is, 10. Let's try 2. And that's 5. Let's try 3. And that's 15. Now let me try to fix something really quick here. When I'm going to come here, I'm going to say null. And I'm going to come here and do the same thing, equal null. And then if that's the case, let's give this a try now. What I'm going to do, I'm going to take those away. Well, he doesn't like it a bit. Maybe I need to come here and type null again. Okay, this is okay, this is okay. Okay, now let's run it again. Now, the no definition default argument. Oh, okay, I think I know. He needs to have a default argument, so I'm just going to go ahead and do that just for the sake of it. I'm going to copy this. Let me just run it to you. Here it is. Redefine a default argument parameter with one argument. You know what? Let me just do that if that's how it works. Let me take this away. Take this away. It should work. I don't know why is he complaining about this. I'm just going to create another type of arguments with no data members, just the data itself. So I'm going to copy this, put it here, and I'm going to take all this away. Just keep one data member. Save it. I'm going to do the same thing here. Copy this. And take those away. And by default, I'll set those to null. And this to null as well. And now if I go back, it should be gone. Everything should work perfectly fine. Okay, so this will be the end of the first class. Now we need to create a new class, and the class that we're going to create is called the binary tree. So just like we did here, we had the header file and this implementation file. We do the same thing with the binary tree. To save some time, I just decided to create that binary tree really fast. I didn't put that much in it, but the binary tree is going to look like this. So at the beginning, I do have my preprocessors. If not defined, define. I'm including the header file for the node. And here's my class. It's a binary tree class. I got protected section, public section. I'm using protected because I'm going to inherit this class in the future when we're going to talk about binary search trees. So the protected element that we have here is a pointer to a node, and we're going to call that the root. Now, for the public section, I do have 3 constructors, and I have the destructure, and I have a friend method to overload the operator of insertion. Now, for the binary tree default constructors, I'm going to set the root to point to null. With the 1 argument constructor, I am actually going to use R to store inside the root. And then for the third one with the 3 arguments, what I'm going to do, I'm going to be passing the data for the root, and then I'm going to be passing 2 binary trees to the left and to the right. Now, what I do here, I created a list of 8 methods that I need to implement. I need to know, how do I get the sub left tree? How do I get the right subtree? How do I get the data of a root for any of those trees? I need to check if it's empty. I need to check if it's if there is, if the tree is I need to check if the node is a leaf. Well, a tree or a node, basically, since we're going to go recursively through the nodes, for every single node is going to be treated as a tree. That's why I say I need to check if the tree is a leaf. And by tree, basically, we're talking about a subtree. And then I have to print the tree in a pre or post or in order if I want to. And then after that, I need to get the height of the tree, and I need to get the number of the nodes. So those are the methods that I need to implement. I'm going to go ahead and do them one by one, but let's go ahead and see the implementation for those 4 methods or 5 methods first. So I'm going to have to go to the binary tree.cpp, and here it is. For the binary tree, null is going to be assigned to the root. That's the default constructor. Argument constructor, the R is going to be assigned to the root. And for the other constructor here, which is basically I'm passing a binary left and a binary right. And if basically what I'm saying here, if you're going to create a binary tree and with the 3 arguments, and you're basically just going to pass the data without passing a left tree or a right tree, the default constructor of a binary tree is going to be called. But if you're going to pass something, it's actually going to ignore this part and it's going to use it. So I'm going to show you, of course, how is that going to work. But let's just go ahead here. This is a binary tree that I have the data, and I have a left subtree and a right subtree. And by default, if no arguments are passed, they're going to be a set. You're going to call the default binary tree. So basically, the left child and the right child is going to be pointing to null. And if that's not the case, you're actually passing some trees, they're going to be used. And here's what's going to happen. I'm going to create a new node. I'm going to use the data for this node. And now, for the right side, again, remember here, when we talked about the node, if I go back to the node constructor, here it is. I have 2 nodes, one of them to the left and one of them to the right. And here's what I'm doing. I'm telling you, take the root of the sub left tree, and for that, the root for that subtree, and assign it to the left node, and do the same thing for the right node. So if I go to the implementation file now, you'll be able to see that I created a binary tree and a binary tree. This time I'm just creating 1 node that I'm passing. And here I'm passing a data 30, and I'm passing a left child and a right child. And of course, I forgot to talk about this method, which is operator overloading for insertion operation, just like we did there. But this time I am going to actually go to the BT, which is a binary tree, go access to the root, and for the root I want to have access to the data. So this basically will show you the data of the root. Okay, now we need to start thinking about those methods. We're going to go through them one by one. Okay, so let's look here. I do have the list of methods that I showed you before. Now this time I added the prototype of each one of those methods here. So let's go ahead and try to get those get left tree and get right tree. So we have the prototype here, and we got the prototype here. Now if I go to the implementation, I will see it here. So this is, where is it? Here it is, get left and get right. Now, the issue that we need to think about here is if the root equal null, that basically means there is no left or right child. So we need to go and start with that. And we'll just say if root double equal null. And we can just see out. Well, actually, it should return something. So let's open a curly brace. And we'll see what to do here, but for now we're just going to have to return a binary tree. Now what is this binary tree? Let's open a parenthesis, and now root of left. Now of course that left could be a tree or could be just a null. Either way, we don't care. As long as the root doesn't equal null, we're going to return that. And in this area, what I'm going to do, I'm just going to show a cout, and I will just say get. Let's any message. Let's say root. Oh, so node does not have a left tree. And let's put and line semicolon here. And that's it. So if you want to try to get the left tree, I don't know, I'm just going to have to keep going and keep working until I figure out if this is going to cause a problem later on. I have a feeling it will. So let's just keep going. Now I'm going to come here, and I'm just going to have to do the same thing here, and I'm going to check the root and see if it's null. And let's say node doesn't have a right. Let's see. Well, actually, I think I should actually it's not the node, it's tree or a subtree, and same thing here. Tree doesn't have a left tree. Okay, let's just type there is no left tree, and there is no right tree. And let's type that here. So we got those two methods now. I remember it's supposed to return a tree, and that tree is going to be the root, whatever is at the right here. And remember, root by itself, it's a node, and if you go to the node, we know every single node has a left and right pointer, so that's basically what's going to be returning. Okay, so we're creating a binary tree. We're using the left subtree to return it, or the right subtree to return it. Okay, so let's see if we can actually use those methods here. So in the source file, let's imagine I'm going to create a binary tree now. I'll just call it temp. And temp is going to equal b1 dot get left tree, semicolon. And let's do the same. This is going to be, let me just run it after that. So if I go down here and create temp, cout temp, and line, semicolon. Now, as you can see here, B1 is the left tree of, so this is supposed to be B3. So B1 is supposed to be left tree of B3, and we know that the value is 15, so I'm supposed to see 15 here. The last one to be 15. Oops, let's see, why is he complaining? Oh, of course, because I got a lot of other methods that need to be implemented. So let me just go ahead here and put return 0, and this is return true, return true. This is void, this is return 0. Copy this. Okay, so this should be okay. And here it is, 15. Now, if I ask him to show me right tree, I'm supposed to see 25. Uh-oh. What did I make a mistake with here? Get right. And again, I think I should supposed to be keeping this uppercase R. And here it is, uppercase R. Okay. Let's see what's going to happen now. And here it is, 25. Woohoo. So we got those two methods to work perfectly fine. He's complaining about this, and I understand what is the complaining, because I'm supposed to return a binary tree. Well, if this is true, you're not going to be returning anything, and that will cause a problem, of course. So I need to figure that out in a sec. So let's just keep going with the method. So we got those get left, get right. I'm just going to say, I put a question mark here because I need to test it to figure out how do I fix that problem. So let's just keep it like that for now. Okay, so let's get those three functions or methods, sorry, done. Get data from the root, check if it's null, and check if it's a leaf. Sorry. So first thing first, it's going to be very similar to what we have here. So how do I check? How do I get the data? Well, number one, we need to make sure that, again, it's not a root. So what I'm going to come here and I'm going to just copy this just like I did here. And I'm going to put it here. And I'm going to check again. If the root is a null, then they say there is no data. That's what I need to see here. And then if that's not the case, there's no data. If that's not the case, well, basically all you have to do, return root. Since it's a pointer, we're looking for the data. So this is how we get the data. I'm pretty sure he's going to complain about this as well, which I'll try to figure that out later. Now, how do I check if it's an empty using the null is a null method? Well, again, how do I know if it's a null? First of all, what am I trying to check here? Yep. Well, again, all you have to do here is return root equal null. If this condition is true, return basically is going to evaluate this expression. If it's empty, so it's going to return true, otherwise it's going to return false. So this is how simple it is. Now, how do I check if it's a leaf? Number one, I need to make sure it's not null. Let me just copy. Well, you know, I don't need to copy. Let's just go ahead and do this. I'm going to try to figure out if a node is a leaf. How do you know if it's a leaf? Basically, if you go to the left and you go to the right and both of them are equal null, then basically it's a leaf. And the most importantly, the root itself should not be a null. So I will say if root doesn't equal null, you're going to have to come here and say return, and you would have a little bit long, not very, very long. And I'll just come here and type else return true. So by default, if it's a null, then it's going to be a leaf. But if it's not a null, I'd have to come here and check something. And I'm going to say if root, remember root by itself, it's a node. So left double equal null. So if you go to the left, you go and you find a null. And if you go to the right, you find a null. Well, that's a leaf. If one of them is not correct, that basically means it's going to be false. It's going to return it. So I got those three methods implemented here. In this part, I went back to the source file and I decided to test those three methods for two of those nodes. So B1, I know it's a leaf. B3, it's not a leaf. So I'm supposed to get true here and false here. I know both of them are not null. And I can get the data. I can run it. And you'll see the results. Here it is. Leaf, no leaf. Both of them are not null. Those are the data. Now, let's go ahead and try to implement those two methods. I'm going to leave the print method to the end. Get high and get number of nodes. Now, both of those methods are going to work in a very similar manner, but it's going to include a recursive implementation. So part of it's going to be recursive implementation. So let's go ahead and see, where is it? Here it is. How do I get the high of the tree? Okay. To get the high of the tree, basically, you're going to have to start by checking if it's a null. The root, again, remember, recursively, we're going to call this. So we're going to say is null. Oh, wait a minute. Null. That's my function. And I will say so I'm going to see if it's going to return true or false. The moment you get to a null, this is where there's no more height to add. Remember, you're moving through the nodes from the left and the right, and the moment you get to a node that is a null, that basically means you have to stop at that point. So there's nothing to go further. So I will just say return 0 at this point. So this is going to be my base case, by the way. Okay. Now, otherwise, here's what I'm going to say. I'm going to say return, and look at this. This is extremely important. Let's see here. You put return 1. I'm trying again, remember, getting the high, plus. And here's what I'm going to do. I'm going to call a function called max. Max is going to return the max of 2 values. I'm going to go to the subtree, and then I'm going to go to the right sub left tree, and I'm going to go to the right subtree, and recursively call get high for each one of them. So here in this area, I need to call get. What did I call the function? Get. Where is it? No. Get left tree. Yep, here it is. So I'm going to call get left tree. Okay, so this is my method that I'm going to call. And we know that this method is going to return a tree. And for that tree that's going to be returned, which is the sub left tree, I want you to call get high again. Okay, and I'll do the same thing for the right. So let me copy this, put it here, and we'll say get right tree and get high again. Now, of course, he doesn't know what is max because I think I might need to include a CMath to be able to use it. Let's see here. Yeah, we know max is a method. Like, let me see if I can actually. Hopefully that will fix it. No. Let me check really fast. Okay. Algorithms. Okay, well, I guess that's the right header file. Let's see if okay, now it's fixed. So he recursively going to call the function and call the function here, and the idea here, as you move recursively through the tree, you will always return the max until you get to the base for all these subtrees. And every time you move to one extra level of the subtree, you just need to add 1 to it, and then get the max of the right or the left, and then whatever's going to be returned, you're going to have to add 1 to it and keep going that way. So this is going to tell you what is the height of that tree. Now this is going to be very, very similar. The idea here to get the number of nodes, is that what it is? Yep, you're going to have to do the same thing here. Okay, check if the null, you return 0, that's where you get to the end. And then what do you need to do basically? You need to say return, and then it's going to be 1 again, plus whatever is going to be returned from the left tree and whatever is going to be returned from, instead of max, is just going to be the addition, the summation for those 2 numbers. So I'm just going to put it here. Of course, I'm going to have to update it. So this is going to be get left tree dot get nodes. Control V. Wait a minute. Control C. Control V. And here, Control V. So this is going to be implemented recursively. Now, let's go ahead and give this a try. Now, I know the tree that I created has a height of 1. And I have 3 nodes inside that tree. So let's go ahead and test those methods and see the results of the operation. You go here, and let's say cout b3 dot get height, semicolon. Let's put a space here. And then I'm going to do the same thing. I'll say b3 dot get number of nodes. And of course, end line, semicolon. This should give me a 1 height, or let me see, is it 1 or 2? I think it's, I can remember 1, or I think it's supposed to be 2, and the number of nodes is supposed to be 3. Let's see if this is going to work. Oopsie daisy, where? Yep, I knew it. This is going to come back to bite me. Well, it turns out that I just had a syntax error, and because I copied the max part here, I forgot to replace this comma with the addition operation, and I forgot about this semicolon at the end of it. So let me go back to the implementation and show you. Here's B3. We know B3 is the root for this tree that contains 3 nodes. And since we have 2 levels, because the root and the 2 trees, child to the left, child to the right, and this is going to give me the height, and this is going to give me the number of nodes. And if I run it, I'll get 2 as the height and 3 as the number of nodes. Now the only part left to talk about is how do we print the tree. Now I do have a function called print tree, and the print tree, as you can see here, it doesn't have a return data type, and I am going to pass an integer, which is going to have a value of 1 or 2 or 3, 1 for pre-order, 2 for post-order, and 3 for in-order. Now I will have a method for each one of those orders. I have the pre-order here, post-order here, and in-order here. Recursively, something's going to happen here. So each one of those methods is going to return a string, and each one of them will have a node as an argument, a pointer to a node as an argument, and we're basically going to use that as the root of the tree. So if I go to the implementation, you'll see here that I got a switch statement for the case of C. I got 1, 2, 3, and there's the default case, just in case you pass something that it's not one of those 3 options. So if you choose 1, you're going to call the pre-order, you're going to pass the root of the tree. If you choose 2, you're going to call the post-order, pass the root of the tree, and the same thing for in-order, you're going to pass the root of the tree. Now, all of these methods are going to look almost the same with a little bit of a change. So what I need to do, I'm going to go show you how the pre-order works. And then after that, we are going to see how the other ones. I already created the code for all of this just to save some time. So I'm going to jump straight to the pre-order, which is this part here. Let's go up a little bit. Okay, so here's my method. So as you can see here, I'm passing the root at the beginning, a pointer to the root as the argument, and I create a string here. There's nothing assigned to that string at this point. Now, I'm going to check if the root doesn't equal null. Now, this is a pre-order. Remember, with pre-order, we go, let me try to remember, we go the root left, right. That's the order of the nodes that we're going to go with. So you print the root, and then you go to the left, and then you go to the right. So I'm checking for, at the beginning, if the root doesn't equal null. If that's the case, then immediately show me the data of that R element, which is basically in the root of the tree. Now, after you show me the data, you go and check and see the left side. If the left side doesn't equal null, I want you to print a space, and then after that, call the same function again. But this time, look at the node that we're going to try to pass this time is going to be the left. As we know that the R by itself, it's a node, and node has a left child, a right child, and I'm going to the left child. And then a pre-order is going to be called here. It's going to go back here. It's going to treat that root as a root for the new subtree, and it's going to treat it the same way until I get to the null. The moment you get the null, you go back to the right side. When you check the right side, again, as long as it doesn't equal null, you're going to have to add a space and then follow the space with a pre-order calling to the right. Now, this is how this pre-order works. Now, the post-order, as we know, post-order basically left, right, and then you see you show the root. So basically, it's going to be very similar to this one, except the part that you're going to print the data itself. And if you look here, first of all, here you start with a space, and then you call. You start with the data, and then you have a space, and then you call the function. A space, you call the function. Now you start with the data, show the data for the left, follow that with a space, and then you show the data for the right, and you follow the space, and then you're going to show the root itself. So as you can see here, check if the root doesn't equal null, and then you go check to the right. If the right is not null, you're basically going to recursively call the function, and every time whatever str you have, you're just going to add to it the result of the recursive call for the post order. Same thing here. Now, if you go to the in order basically means it's left root and then right. So you can see here, I have something in the middle, and this is the left, this is going to be the root, and this is going to be the right. The order here is very important. As you can see, I put a str at the top, and then I put the value, a space, and then the root, and then a space, and then a value. The order of the spaces are very important. Let me show you here. Data, space, and data. This is for pre-order. For the post order, data, space, and then the data. And here, you got data, space, and then the data, and then space, and then data. Now, those are the three methods, and let me just go and show you the implementation. What I did here, I created this subtree, I created another subtree, and then I connected those two subtrees with this node B. What I'm going to do, I'm going to show information about B most of the time. So I'll put B here, get the right tree. Okay, what is he trying to do here? This is going to show the data of B. I'm not really, I'm going to give them a test later, but for now, all I care about is the traverse, which is this one, print the tree. I'm calling 3 here. I can call and do 1 if I want. Let me just take those away. I don't want to see any results. I just want to see the result of this operation. Now, just to visualize the tree that I have here, it's basically going to look like this. Let me just open the painter. The tree is going to look like you have 1,000 here, and then you go to the left, you have 30, and you go to the left, you got 15, and you go to the right, you got 25, and then you go to the right, you got 300, and then you got here 150, and then you got here 250. So this is my tree. Now, the first thing I'm going to do is the pre-order, and the pre-order basically should go 1,000, 30, and then 15, and then 25. So I'm done with this part, and then 300, and then 150, and then 250. Again, remember, this is a pre-order. So you show this, you show this, you show this, and then 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 you show this. Let's go ahead and give this a try. Run it. Remember, I called the pre-order here. So here it is, 1,000, 30, 15, 25, 300, 150, and 250. Let's go ahead. This is the results, and I'm pretty sure it's very similar to the results that I have here. 1,000, 30, 150, 225, 300. Okie dokie. Let me do the post order now. Post order, as we know, it's supposed to go left, right, and then root. So I'm going to have 15, 250, 25, 30. So I'm done with the left side. And then you go to the right side, which is going to be 150, and then 250, and then you go 300, and then you go 1,000. Well, let's go ahead and give this a try. So post order is supposed to be a number 2 here. Let's run it. And I am going to open the painter and the results. So 15, 25, 30, 150, 250, 300, and 1,000. So that is correct. Let's try to do the same thing here. Now we're going to go in order. In order basically means you're going to go left, root, and then right. So it's going to be 15, 30, 25. So I'm done with this part. I go 1,000, and then I go 150, and then 300, and then 250. Let's go ahead and change the setting here to be 3, and let's run it. And let's push this down, push this up, and you can see 15, 30, 25, 1,000, 150, 30. Okay, it looks like it's working. I'm going to post the code with this, of course. Let me see if I can get the height of B and the number of nodes of B. See if this is going to work. Now, from the look here, the height's supposed to be 3, and the number of nodes I should have are 7. Let's see if that's the case. And here it is. I got 3 height and I got 7 nodes. Of course, I can give the data for anything, but yep, that's pretty much it. So again, I'm going to post this video, of course. I'm going to post the code for it. You will need this code to answer some questions that I may ask about later. Let me know if you have any questions. Goodbye.